Okay. So this is about learning something actually useful, finally, at this school. No, I mean deep learning something useful, not learning. So I just propose to that you open the notebook and click a few first cells, because it will actually take a while to load. And most of this notebook, so you can see there's a lot of code. So what is this tutorial really about? It's actually about learning meaningful representations with spiral convolutional neural networks. And the spiral convolutional neural networks, they actually revolve around a really peculiar idea about what a convolutional what a convolution could be like on a mesh data structure. So this is gonna take a while to load. So with spiral convolutional neural networks, this is how the convolution is defined. So as you can see, what do? We actually start with a mesh. We pick a point in the mesh, and then we iterate along the first string, then along the second string in a very specific order by traversing this mesh via a spiral path. So you can do that on images too, like it is shown here on the right. Note it's very similar. So we can actually enforce these traversal paths on meshes, on real meshes even, but for that they need to be of fixed topology. And there are meshes, there are collections of meshes of fixed topology. For instance, the meshes that were acquired during the Faust project at NPI Tübingen. So Faust project is the data set consisting of scanned individuals of, I think, a few dozens of individuals. We can actually look
Currently, surface registration methods are evaluated on synthetic datasets, which lack realistic definition.
It doesn't matter what they did. The point is the result, actually. So what they did is they asked a few dozen individuals to stand in different poses while they were scanning them using state-of-the-art cameras and depth sensors. So what they did is they obtained these meshes that are actually highly realistic. So this is what you could do with the state-of-the-art imaging systems. And they have asked people, several people of different, appearance, and basically to do different actions, like these actions. Okay, there are a bunch of them, and they have split that into test and train data sets that don't intersect, and they have published all that. So we will be working with just this kind of data. So it turns out that there is a template mesh for all these scanned people. There is a template mesh that consists of roughly 6,000 vertices, and you can compute how many triangles there are. It's a triangulated mesh that serves as a template for everybody else, for every other meshes, actually. And what we will be doing is we will be processing these meshes. So I have told you about the way of defining convolutions here, but what we will be actually doing is we will be actually doing arithmetic in the latent space. So let me just check quickly. This is also a tutorial that has been designed in such a way that you can do it on your own, at home even. But let us do a quick walkthrough of that. For that, I will ask you to click on the next couple of cells here. So these are the imports. You don't have to type in anything. We will require a GPU for that. I'm given Tesla K80 actually. And let us just quickly view the meshes that we will be working with. So this is the type of mesh that the kind of mesh that we are working with. So this is a scanned mesh of a woman. So you can actually zoom in and see that it's a real mesh actually. This is a special function for mesh visualization. You supply it with vertices, and what it does, it pulls up a template mesh, assigns the vertices, and renders it. So all the meshes are actually the same topology, the same connectivity. They are the same graphs, but the positions of the vertices are different. This is why you only put inside the vertices. So this dFaust dataset or dynamic Faust dataset is 40K scans of 10 different people that perform some actions such as leg and arm raises, jumps, and so on. So what we will do is we will train actually a mesh convolutional auto-encoder on this dataset. So we will not train that because it just takes a long, but we have trained that for you. And let us just click a little bit further. These are the settings. So this is the class for the data set. I'm just clicking it. You can read it carefully at home if you like to. This is the mesh convolutional operator, the spiral convolution. As you can imagine, it will only work if you have a fixed topology mesh like this, and it will not work if you have arbitrary meshes, including non-manifold meshes that still occur in real world, of course. I wish I could show you some of them. They're really creepy. So this is how the spiral convolution is actually defined. Imagine you're having x sub I that are vertices that are ordered in a specific way. So f of x sub I here is the feature of the vertex x sub I. Here it's x sub L, okay? So this is the mesh convolution that is defined by just weighting, not weighting, just you know, basically computing the inner product of the feature vector with the filter kernel as usual. So this can be actually defined as a matrix multiply operation or via a linear function, a linear module in PyTorch. The thing with these spiral convolutions is they actually they actually enforce a very specific ordering of this sum here. The first vertex in this order is the geodesic first nearest neighbor, and the other is obtained by traversing the D ring in a specific order. So you can define a spiral patch operator just in the very in a similar sense as we defined patch operators before with these local coordinate systems that everybody was very interested about. So we define the spiral patch operator by just it basically accepts a vertex and it spits out a sequence of vertices that form a spiral around the input vertex. So h is the patch radius. So the spiral convolution is actually just a convolution with this sequence of vertices, with the features that live in the vertices in this sequence. So there is this spiral conf module that has been pre-implemented for you. You don't have to type in anything. The exercise is not that. So it is pretty versatile. It accepts a lot of activation functions, and what it actually accepts is this mesh and the adjacency matrix. And then it does everything by its own. So let us just click the cell and proceed further. So the uniqueness is basically given by fixing 2 degrees of freedom, the direction of the rings, which is counterclockwise, and the first vertex, which is the closest geodesically vertex to the given one. Okay, so I hope that you get a rough idea about what a spiral convolution is. If you want to know more, I encourage you to read the 2 papers. One is the neural 3D MM, with MM being the morphable model here, and the other one that also proposes spiral convolutions, but with a different topological ordering on the mesh. So there is another paper. They are referencing each other. I believe they at some point were a bit of rivals. It doesn't really matter a lot on which exact convolutional operator you build your neural network, as long as the convolution is consistently defined. So here we will be working with the spiral convolution, and that's okay if you work on a different type of convolution, like the edge convolution that we were talking about before, or any other new convolution that you will be able to define. Yeah, so what we will do here is we will build a neural mesh autoencoder. So I think that most of you are familiar with the concept of the autoencoder. So what an autoencoder does, it computes some encoding in a Euclidean, high-dimensional Euclidean space of an input data. For instance, here it will be a mesh, but it also can be an image or a text or a graph in other cases. So it embeds this object into a high-dimensional space. So this is called the encoding stage. So thus we will have to be given an encoder part here. And then it decodes this latent code into this very object that was obtained, it basically reconstructs this very object. So the goal is, of course, to reconstruct as precisely as possible in the geometric sense in our case. So we will be encoding the mesh into a high-dimensional Euclidean space and then decoding it back into this 3D space, into the space of all meshes. So here we have the spiral autoencoder. This is a lot of code here that we have just actually copied from the official implementation here, and the way we didn't rewrite it is that to show that we don't really care about the specific parameterization of an encoder-decoder network, but what we care about is the latent codes that we obtain by training it, and also because there was a pre-trained version. Then we just also define the class that will hold the data for us, along with the data loaders. So please don't be scared about the amount of code here. It's really easy code. It's not very easy to read, unfortunately, but it's very easy to understand. What it does is just a standard deep learning encoding decoding pipeline. So if you're not very familiar with that, I just encourage you to read the deep learning book by Benjo and colleagues. And let us just train the network. In fact, we're not going to train the network actually, but rather we will load the pre-trained network and start with the exercises. So note here that we'll have to pre-generate the spiral paths for the convolutions. Because all the meshes have the exactly same topology, it is possible to pre-compute the sequences of vertices that we traverse along while doing the convolution. So in our encoder-decoder network, we actually have 5 levels of convolutions, just in the same way as in image convolutional architecture. So for example, as you remember, the AlexNet network had 5 levels of convolutions too. So the first level of convolutions start at 6,000 vertices, then we do a pooling and we are left with 1,700 vertices, and so on and forth until we arrive at the latent code. And then what we do is we reconstruct back by unpooling and convolving with transposed convolutions as usual. So here we'll transfer all these spirals to the GPUs, build the model, the optimizer, and the loss function, instantiate the model itself. Note, I'm not filling in any of the cells, and neither should you. It should just work at this time. So here is the actual architecture that we are actually using. It's you can see it's a really straightforward thing. It's actually the encoder is actually a sequence of convolutions with activations. Then there's some transformation in the latent space that actually projects to 16-dimensional hidden representation. And then there's the upsampling layers of spiral convolutions again that reconstruct the XYZ positions of the mesh vertices. So because topology is fixed, all we are operating on is just the mesh vertices. We are not doing anything with the topology except for extracting the spiral paths here. Exactly, yeah. Because they are the same meshes, the same. So, for instance, what does it mean that they are the same meshes? This means that the for people who stand like this in the dataset, the tip of the finger is the same vertex ID as for people who do like this. So they are connected by a non-rigid deformation, but the mesh vertex ordering are the same. In this sense, they are the same meshes. This is why the same spiral paths will generate the same sequence of vertices. Yes, but it's true. But here the spiral paths have been generated for the template mesh only, which is a neutral pose, and has been transferred to the default. Yeah. Okay, so as you can see, it's a very simple architecture once you have defined the spiral convolution. So with training the network, we provide the code, but we don't do the training because it takes so much time. As usual with deep learning, what we do is we will actually run the testing. That is, we will produce inference for all of the meshes in the test data set. And now the goal will be to work with the latent space. So I think that most of you are familiar with the relations, with the encoder-decoder architectures and the latent representations that they compute. Here we are embedding our meshes into a 16-dimensional space in our case, and computing the latent codes in this 16-dimensional latent space, because similar meshes should be embedded and reconstructed in a similar way. This will mean that our structure of our latent space will be roughly Euclidean. That means that nearest neighbors in the latent space should correspond to to similar meshes in the mesh space. So what we first will do is we will try to just sample from the latent space of mesh encodings that we have created here. So your exercise here is to generate a random 16-dimensional vector using PyTorch and use it to decode the underlying shape. There are also a few hints on the random states and lucky seeds here. So what this should look like in the end, you should be able to sample from the latent space by inputting a model and also the shape data mean and shape data std variables. So running this cell each time should produce you a different and random mesh that will look exactly like some of the meshes in the dataset. So let us just try and do this. So what are we doing is that first we will have to generate a uniformly distributed random vector of size 16. So R is, let's say R will be numpy.random, then it should have a uniform method, and then let us generate the latent code like this. That should be a result of this numpy r.uniform. Let us say that it will be from -5 to 5, and the size should be 16. I'm not sure if the keyword is the size though. So now we will have to turn that into a matrix of size 1 by dim. This means that we'll just expand dims on that and insert an empty axis here, and the size is actually dim, so dim here is 16. Now what we do is we transform this latent code into a torch latent code. Just wrap that into a torch tensor and transfer that to, let's say, model device. And you can correct me if I am doing things wrong. So the second thing would be to decode the latent code. So we are given the latent code underscore torch. So we will have to do the model decode So I decode here. So the model is an instance of this mesh spiral autoencoder class. This is this means that it has this decode method. You can check it out. It really does have this decode method. So what decode does, it accepts a latent code and it outputs you actually the mesh, or rather a batch of meshes. So then we'll have to detach it, transfer it to CPU, and convert it to a NumPy array, and assign it to a decoded mesh variable. Also, because decoded mesh is a batch, actually, this means that we will have to squeeze out the batch dimension, and there's this last tricky part. Will not include the last point in this mesh. This is to ensure the same dimensionality between the decoded mesh and the mesh mean. Now, what we will have to do further is we'll have to basically multiply the decoded mesh by mesh std and add the mean mesh here. And then we will return the decoded mesh. I hope that Albert can fix me if I'm wrong. Yeah, I'm roughly not wrong. Okay. I'm gonna wait for a couple of minutes before you type the solution. You can, of course, you can launch the solution notebook as well and just copy the solution over. So once again, what did we do? We have created a random vector that belongs to the space of latent codes of our model, and we hope that our model will be able to correctly decode this code into a correct mesh. We are only producing out the vertex positions here, so decoded mesh is actually 6000 by 3 array of vertex positions. Furthermore, this model produces us the vertex positions in a normalized space. This is why we are multiplying it by mesh std and adding mesh mean. I am absolutely not sure that it will work, but let us try. It actually works. So I'm a bit surprised, actually. So because this is a random mesh, it is a valid mesh, so don't be very scared about this mesh having this rubbish because instead of the arms, from time to time, it reproduces bad results in terms of visual quality, but from time to time, it reproduces a really nice result. For instance, there's this lucky seed that they actually used in the paper. So rand is a random number generator that you are very much into, I believe. And this is a lucky seed. Oops. It tries to run away from me. If I'm putting this random state here, I will be given a type error. Random state. Oh, sorry, that's the rand. I should assign it to the rand. Right, so this is a much nicer mesh. So Albert has been spending hours to get this. Sorry. So as you can see, so this is actually a mesh where even the fine-grained details such as fingers are mostly nicely preserved. But otherwise the mesh is of course noisy because it is still, you know, random in some sense. But mostly what you will be getting here is you will be getting all sorts of ugly meshes. So you can try that for a few times. You will be getting meshes in non-trivial, non-neutral positions because they were encoded by the encoder and they were seen by the encoder. So when your random seed happens to be generated in the portion of the latent space where there are meshes with, you know, raised hands or raised legs or other poses, it will still decode you a mesh in a non-trivial pose. So for instance, this man is a little bit you know, bended forward or whatever. So let's try just one more time again. This is more like a woman mesh. It wasn't able to actually nicely represent her right hand. It's too short, but otherwise it's a mostly valid mesh. And it also has some kind of a slightly non-trivial pose. For instance, the spine is not straight, as you can see here, and also the hands are not in a neutral pose. Okay, so let us proceed further and explore separate directions in the latent space. As you remember, what we have actually done is we have actually generated 16-dimensional random vectors. So out of these 16 dimensions, most of the dimensions should mean something. So large values along the first dimension should be meaning something. For instance, let us explore what the latent code means by itself. Which transformations correspond to subjects with raised or lowered hands, to subjects leaning back or front, to gender, and so on and forth. So what we will do is we will basically manually edit the code. So let us back up the code. Then we will create a copy of the latent. We are creating the copy and backing it up, and then what we will do is we will manually edit the code and assign a large values to some of the coordinates in this code here. So all we do is actually we assign like +10. Let me emphasize the plus here, and we decode that. So so this is a weird pose. This is obviously an exaggerated pose here, but what we can see is really a weird pose, right? What we can see and try to remember is that this is this kind of a pose. Let us assign this same code, the same coordinate -10, which is like an opposite direction, an opposite number. This is a very different pose and a very different mesh. Okay? So I encourage you to spend just maybe 5 times Sorry about that. So I encourage you to just spend maybe 5 times tweaking the coordinates in this space by doing the same. So you pick a coordinate, say you pick coordinate number 9, you assign it +5, and you render the mesh and you try to interpret what's going on. Doing that, you will be able to actually see which coordinates correspond to which poses and which properties of the mesh. you will of course note that the latent space is basically, first, it's non-linear, and of course the coordinates do not instantly explain all of those things that will be happening to meshes. To look at the coordinates more closely, what we should do is we should rather compute a principal component analysis on the latent space embeddings, like we did in the manifold learning tutorial with the faces. So has anybody found which dimension corresponds to subjects raising their hands? Or legs? Or the gender? So for instance, I have discovered that this latent coordinate number 2, if you assign it to -10, then the subject tries to raise his right leg while generally maintaining this neutral position otherwise. So maybe you have discovered the same. What happens to the hands? Yeah, I think that hands are damaging because they have a high frequency geometry associated to them. If you just zoom into the fingers on the legs, they are basically crap too. Yeah, but because most of the mesh is actually smooth, and it's relatively easy to learn smooth signals and not the high frequency signals, for some reason, for this architecture at least. You can also look at the subject's face, and you will note that it is also somewhat noisy, especially the ears and other high frequency details such as the lips. They can be noisy as well. But the hands, they are generally really misrepresented. To be honest, I don't have an answer for that. I think it's a good question. I don't know. There can be different hypotheses. I don't know. I don't think that because spiral convolution is actually doing really well on this. Okay, because the spiral convolutions don't fail to represent, the other parts of the mesh. I have no idea why it should fail on the fingers like this, and it doesn't fail in some of the cases. It's just a noisy mesh. I think this is because compared to the, well, it has to reconstruct the mesh by training the autoencoder. Then the error that you get, the reconstruction error that you get on the fingers is really low. So it doesn't care about the fingers, really. What it cares about is the large body parts. Okay, let us compute temporal relations between poses, and for that we will have to load the test portion of the dataset and select two poses, the non-neutral pose of a female. This is the pose with a raised leg. Okay. And a neutral pose of the same female. We selected that by hand from the dataset. This is actually the neutral pose. Okay. Another thing, I have created the Encode mesh function. That is a helper function that basically encodes the mesh into a latent space and returns you a latent code that is a torch tensor. So you can encode the mesh by this function and decode the mesh by a function that was in the previous cell. So let us encode the latent poses of that female mesh, and just obtain two latent codes for the non-neutral pose and for the neutral pose. So let us try and alter these poses a little bit. So for example, we can interpolate between the two poses. Let us program a pose interpolation function to build intermediate shapes that have been never seen during training. So it's really easy. What you basically do, you have to program this function, interpolate between latent 1 and latent 2, and W1 and W2 are the weights in this interpolation, respectively. So all you do is you multiply the latent by this first weight, and you add it to a latent 2 multiplied by the second weight. Okay? That's what we have. So, for instance, we have this. Let me show that for a while. Let's say we have the non-neutral pose and the neutral pose, and we want to compute an interpolated pose by assigning a weight 0.9 to the first non-neutral pose and 0.1 to the neutral pose. So what do? We basically compute a convex combination of the two, and we decode that. So we compute the convex combination of the latent codes in a latent space, in 16-dimensional Euclidean space, and we decode that into an interpolated mesh. So as you can see, this is a mesh that is close in shape to the non-neutral mesh, where the pose has been to raise the leg. If you lower the weights like this, you will see how this mesh gradually interpolates towards the neutral position. So this is 0.8, let us do 0.4 and 0.6 here. So this is already roughly the neutral pose, except that the back has not been straightened yet, maybe. Yeah. So you can do a movie if you wanted to with this kinds of interpolations, and it's going to be really smooth. Another thing that you could do is you can actually extrapolate. So you can interpolate with sort of negative weights, right? So let us remove this code portion. So what do is we actually copy the code from here, and instead of computing a convex combination, we compute the same convex combination but forget about positiveness of the weights. So for instance, you could compute a convex combination that is going to be a linear combination or a affine combination of this. So for instance, the weights should still add up to 1. This is going to be weird. Yeah, this is going to be weird because what we are trying to do is we are trying to extrapolate beyond the normal pose, but because the pose is already normal, it is trying to extrapolate to something weird. So let us do it in the other directions. Let us extrapolate beyond the non-neutral pose like this. So you assign a weight of more than 1 to the non-neutral pose. So this is really a more extreme pose in this case. So as you can see, first it really it extrapolates nicely beyond the non-neutral pose. This is a pose that has never been encountered during training. So people have never asked subject to raise their legs this much high. But nevertheless, the model can generalize to these poses too. It will, of course, leave rubbish on the on the fingertips and on the toe tips, but otherwise the general pose is pretty precise. And the last thing that we will do here is we will do the pose transfer. So let us load a neutral pose for a male. So this is also a hand-selected mesh that represents a male in the neutral pose. So what do we want to do? We want to make this mesh raise their right leg. So how do we do that? Let us actually compute the difference between the neutral latent code and the non-neutral latent code for a female pose, for the female, for the female pose. So what we'll do is first we'll compute the mesh encodings for all of the meshes that we have. So we compute the latent code for the female pose with the raised leg, we compute the latent code for the neutral female pose, and we compute the latent code for the neutral male pose. So 3 latent codes. 2 of them are female, the other one is for male. So let us compute the difference between the first 2 latent codes. So let us compute the difference between the latent female pose and the latent female neutral variables. So what does that encode? That encodes, well, basically the difference in some latent space. We hope that because this was the same female subject and the only difference was in pose, that this is a universal difference in the sense that if we add that to the latent male neutral pose, latent code of the neutral male pose, we will obtain something close to the latent non-neutral male pose. So let me just show you what we'll have. So let us decode that and display that, and this is what we have obtained. So this is actually the pose of the male that has been decoded from the latent space. So I think that I hope that everybody understands what we have done here. Yeah. No, that works generally for, first of all, of course it works best for meshes of the same subject. So if you have an information about the subject, it is easier to define and compute the latent codes that summarize these motions. Because if you have a neutral pose of a man and a neutral, yeah, so. Yeah, in this case we have found that manually, and you can try it with a different male or a different female. It will look comparatively nicely. Yeah. It's not exactly cherry picked. So this is pretty much it with this tutorial. As you understand, I wasn't going to describe all the spiral convolution implementations in detail because it's too much coding and we won't be able to cover that anyway. Instead, we focused on the latent space arithmetic. And so I hope that I was able to convince you that with the mesh autoencoders, we are able to obtain very powerful and descriptive representations, latent representations that are easy to manipulate, actually. So, so I think that we can rest now for the break and for the 20 minutes. And or you can ask me questions. Yeah. Exactly. Exactly. Thank you. Absolutely. It's mostly visualization, though. Okay. That's it.